Okay, so welcome back to everybody. We start the booster session on natural language processing and digital humanities and natural language processes and social media. So I thank the speaker and ask them to be as quick as possible. Okay, less than 5 minutes if possible. Thank you.
Good afternoon, I'm Rachele Sprugnoli from the Digital Humanities Research Unit in Fondazione Bruno Kessler, and I invite you to come to our poster that is about KD. KD is the acronym for Keyphrases Digger. It's a rule-based system that combines statistical measures and linguistic information given by part-of-speech patterns to extract a weighted list of key phrases from texts. A key phrase is an anagram that captures the main concept of a document or a set of documents, so they can be both single word and multi-token expressions. KD is a reimplementation of the previous FBK system for key phrase extraction, and we had 3 main challenges. The first was to improve the tool in terms of precision recall and F-measure. The second was to speed up the processing time of the tool, and the third was to enhance the customizability of the tool. As for the first point, it is the improvement of extraction performances. We evaluated the KD on both English and Italian and on 2 types of texts. So we replicated for English the SEMEVAL 2010 evaluation on key phrase extraction for scientific papers, and KX achieved the 7th place, whereas the KD achieved the 2nd place, just after the best performing system, that is a machine learning one. For Italian, we asked a historian to manually identify a set of key concepts for the De Gasperi corpus, so the writings of Alcide De Gasperi of the last century, and the precision of KD over this list of expert key phrases was of 42%. For processing speed, we run both tools, KX and KD, on the same machine, on the same corpus, and with comparable settings. And as you can see, KD is extremely faster than KX. So this improvement makes the integration of KD in web application possible. Customizability is achieved with a set of features. KD accepts as input a wider range of preprocessed text and also raw text from for English. The user can customize many configuration files, use different options, and the tool is also easily extendable to other languages and to other part-of-speech tag sets. KD is already integrated in our Alcide platform, so it is already been used by a group of scholars in the humanities. We also have an online demo, so the user can copy and paste the text, can choose among some parameters in a very simple way with a very simple interface, and have the output in 3 different formats, a tab-separated file and 2 visualization. And we also have just released the software package, so you can download and use it and also integrate it in your applications. You can find the package on our website. Thanks for your attention, and see you at the poster session.
Good afternoon, I'm Marco Stranisci from University of Turin, Department of Computer Science. I'm here to present an analysis on the school reform, on the online school reform. Our work focused on La Buona Scuola, that is the name in which the school reform is better known, and we do this research to analyze the online debate through the development of a corpus of more than 6,000 tweets annotated for sentiment analysis. We decided to focus on this topic because Renzi's government created a website to do an online debate aimed at collecting opinion from citizens. And so we had two resources, two datasets. One of tweets collected from 15th of September 2014, and one of to the 15th of November 2014, and a dataset of text from the consultation website. These texts are very interesting because they were already annotated both for polarity and for topic, as you can see in the slide at the bottom of the slide. So we have two resources for comparison. Having this, we have worked for the annotation of the Twitter corpus. The annotation stage was aimed at focus on three dimensions: the polarity, the presence or absence of irony that was polarized, and the topics. We chose 13 thematic labels from the website. The most used 13 thematic label from the website of the consultation, and we use it for a thematic annotation. The inter-annotators agreement was Kappa 049. What are the results? The polarity analysis showed two important findings. The first one is that in the graph on the left, you can observe the distribution of polarity on the Twitter corpus that shows a high number of non-labeled tweets, and that a very big number of negative tweets than positive ones. They are 3 times more. Otherwise, in the distribution of polarized polarized label on the corpus of the consultation by government Renzi is more balanced. Why? We believe that the difference in this distribution of labels has to research in different social contexts, in the fact that these two sites are two different social contexts that influences the user's utterances. The last slide is the topic analysis, and we have two general findings. The first one is that the annotators of the Twitter corpus labeled the most part of tweets with the generic tag Buona Scuola. So the argument that were discussed on the government consultation wasn't found in the corpus of tweets. The last one is that the distribution of topics varies even so much from one corpus to another. You can observe the recruitment topic that is very bigger than in the Twitter corpus than in the consultation website. Thank you for attention.
Okay, good evening. My name is Evgeny Stepanov, and I'm going to present a poster today, which describes the work of sentiment polarity classification with low-level discourse-based features. So when you open any paper on discourse parsing, and here are two examples, you see that discourse parsing has many application areas like information extraction, essay scoring, summarization, and sentiment analysis, and many others. However, there are really few successful applications of discourse parsing. So there are two major discourse annotated corpora for English: rhetorical structure theory And the bigger one, Penn Discourse Tree Bank. Most successful applications are on rhetorical structure theory, and because it has a nice tree structure and it could be easier explored and exploited for summarization and the reduction of text. Penn Discourse Tree Bank, on the other hand, is flat and it's difficult to find the proper use of it given automatic parsers. And there are many statistical parsers developed. And this year there was a shared task on shallow discourse parsing, which turned out to be the state of the art of the winning system. Has only F1 of 24 for end-to-end performance, which really limits the application of discourse parsing. However, when we look at discourse parsing in PDB style, we see that it is a complex structure. It has several tasks with different performances, and given the error propagation, at the end we have a F1 of 34 explicit relations and 16 for implicit relations. Obviously, this is really hard to make use for anything. However, when we take only two subtasks like discourse connected detection and their sense classification, we have acceptable performance. So in our work, we use the output of just these two well-performing tasks and apply it to sentiment analysis. We design discourse parsing, discourse-based features and evaluate them. We observe that even though they have insignificant contributions to a bag-of-word model, which is very strong baseline, it's like a kind of state-of-the-art. We support virtual machines, but the models using just discourse features perform quite above the chance level. So for the further details, please come to the poster.
Okay. Yeah, welcome. My name is Tobias Horsmann. I'm from the University of Duisburg-Essen, and my topic is effectiveness of domain adaptation approaches for processing social media data. And as a start, if you try to part of speech tag data from the social media domain, you usually have sentences like this example here taken from Twitter. And the accuracy you get if you try to text this kind of text is often disappointingly low. So researchers reported something around 76% accuracy on this kind of noisy data if you use some of the available speech taggers. The reasons are manifold. So you have random capitalization, as you can see here, unknown word forms, which might be intended or unintended spelling variations of existing words, missing white spaces, but also missing punctuation marks, or even frequent use of the punctuation marks, which is not really grammatical at all. Research has spent some time in this field already to improve part of speech checking accuracy here. And what we did was a detailed investigation of the single approaches and how effective the different approaches are that have been proposed for improving part of speech checking accuracy on social media. So if you try to tag a part of speech, if you try to fit to the social media domain, you usually start with a small set of annotated data set. You start with a small data set that has been human annotated, and this is usually very small, and human labor is very expensive. So in order to increase the amount of available training data, what you can do for one is use existing tagger and tag raw data with and text these data with several available part of speech taggers, and then simply add those to the training set where all taggers agree. So you kind of have like a majority voting effect and artificially increase the amount of training data. The second thing you could do is using a part of speech dictionary. Again, here in case you encounter unknown word, you try to provide a strong a priori information for this word in case it occurs in the part of speech dictionary, which is the most likely part of speech tag for this word. The next thing you could do is, in case there are already existing resources for some of the very source languages, like English, you can use these existing resources to add them together to the annotated training data of social media, and so start mixing in foreign data to also increase the lexical knowledge and the amount of data you have to overcome the data sparseness. Last but not least, you could, which also has been employed, is clustering. So you cluster about a huge amount of unlabeled data, and then provide distributional similarity information for unknown words, and support the word recognition by providing this distributional information. So each of these individual approach has a certain effect or degree of effectiveness for the task. And of course, you also wanted to know the best combination. So which of these combinations should be combined ideally. And in case you want to know the solutions, then please come and visit me at my poster. Thank you very much.
Good afternoon, everybody. I'm Danilo Croce from l'Università di Roma Tor Vergata. And again, we see sentiment analysis over microblocks, particular tweets. And since our one of our last papers from Calling, we demonstrated that context can be very useful in order to disambiguate the polarity of a single and often very short message. And just see what we mean for context. In this example, I totally agree with you. We are not able to understand which is the polarity of this message, but if we're able to recover the context, so the previous message that have been written and this last message is replied to, we have useful information. And so the idea that we present in this work is that in order to manage the polarity and to recognize the polarity of a tweet, we can usefully exploit the observation of previous tweets, the context, maybe in the reply to chain or otherwise messages sharing the same hashtags. In these works, actually, we modeled this context like a stream of messages, sequence of messages. So the problem was mapped to a sequence classification problem. In this work, we would like to extend this view. So we defined a more complex view because people does not interact like in a simple stream, but people interact each other. So we try to build a richer structure, more complex structure. So we define a graph. I hope you see these nodes of the graph that are the messages. We can add other nodes that are the words that in general appears in those messages. And then we are able to connect each other, these messages, because they belong to the same context. Then being able to connect also words that appear in the messages, we have this graph that we call the contextual graph. By the idea, why graph? What can we do with the graph? We can apply a class of learning algorithm. In this particular, we would like to propagate a polarity information across the graph. So being able of knowing the polarity of words or some messages that can be positive or negative, and some messages that we don't know the polarity, actually, what we would like to do is to let the polarity flow across the graph. How? We investigated several label propagation algorithms over graphs, and we investigated how we can build this graph in terms of the initial polarity, initial information that we assign to the nodes represented messages, the information that we derived through large-scale distributional models of sentiment polarity, that so we can build a huge amount of information to assign to words in the graph. And then we show in this paper that we can improve performance over the classification knowing such information. Thank you for the attention. For any other details, come and see to the poster. Thank you.
I wish to thank all the speakers, and the poster session will take place after this other booster session.
Yes. So we just continue basically with the boosters. So next one is Lorenzo Gregori. Is that you? Can you talk? Yes, please.
Okay, I'm Lorenzo Gregori from University of Florence, and I present this experiment for linking two multi-language ontologies. One is the well-known semantic network that is BabelNet, and the second one is an ontology of action, IMAGACT. And the linking experiment aims to connect the video that we have in IMAGACT ontology with the BabelNet scene set, and so the verbal entries in BabelNet. In the this linking experiment is highly desirable in order to build a rich multimedia knowledge base for disambiguation of reference of action verbs and automatic or assisted translation. And we build up a data set taking 7 English verbs, action verbs, with a high frequency, high ambiguity, and high reference to action. We select 25 IMAGACT video, IMAGACT scenes, and 30 Babel scene set, and we build this dataset with 750 binary judgments. And for each couple, for each pair, scene set, the annotator judge if the scene is appropriate to represent the scene set. We have very good result of this matching, and for the detail of the algorithm we can see you later. And the aim of this experiment is to enrich this bubble scene set with 3D video scenes that are very more effective in representing actions than static images, and to speed up the IMAGACT extension to other languages by connecting a very specific ontology like IMAGACT to a very huge knowledge base like BabelNet. And this is, video is very slow, is a video of beating up someone. But yeah, this is like a possible application, in meaning that an IMAGACT scene that is linked to a lot of verbs can be linked to BabelNet, and vice versa. A Babel scene set can be represented by a 3D video scene. Thank you very much.
So, good afternoon. My name is Irene Russo. I am a postdoc researcher at Istituto di Linguistica Computazionale di Pisa. Since we are late, my presentation will be very short. And basically, I present a work about basing grasping possibility for action. With grasping possibility, we mean a basic classification about how we can handle objects. We can grasp objects with one hand. Sometimes we need 2 hands, and sometimes we can grasp by part, and sometimes we need an instrument. This classification is based on psychological studies and is used in cognitive robotics to model the way robots can learn automatically to have expectation about what they see. So basically, if you think about how you can handle an object, if you want to teach a robot to do this, you can encode this information, or you can try to have some learning strategies. And the poster is about a first study in this direction. We try to combine 2 kinds of information. One is situational properties. And with situational properties, Barsalou means the kind of physical settings and event an object can occur in.
And we compare this information, modeling this information as distributional semantic vectors with basic information about weight and dimension of objects that have been crawled from Amazon, from e-commerce website that contain this information. In this work, we try to combine the cognitive psychology notion of situational property with that of affordance, that it's a psychological notion that it's widely used in robotics and concern the action-oriented, it's a more action-oriented idea and concern the kind of action you can do with an object. So no spoiler about the result in this presentation. If you are curious about which kind of information is more useful for this automatic classification, I will wait for you at poster.
Good afternoon. I'm Flavio from Bicocca, Milan, and in our work we present an algorithm for word sense discrimination. First of all, the starting problem is that language is intrinsically ambiguous and proper names particularly so. So word sense disambiguation tackles this problem, and word sense discrimination is its unsupervised counterpart. Here we want to divide the occurrences of a word in different classes. Each class represents a possible sense of that word. So our fundamental assumption is that context implicitly defines the sense of a word, and we do something akin to context clustering. So more technically, how do we model our context? We are graph-based. We start from a word co-occurrence graph, and we choose of our document, and then we choose a word B to disambiguate. Then we go from global to local, extracting its neighborhood from the graph, its word cloud. Then we filter out unnecessary words, like, for example, stop words or very, very common words. And then we use a weighted Jacquard distance defined on word contexts to pass from the graph to a metric space representation of the word set. And then we can pass from this word space again to a graph, the distance graph, exploiting the fact that the Jacquard distance is limited. So we can build a graph where two nodes are connected if their distance is less than 1. So the key notion is that of gangplank edge, which is not a bridge. So this is a mathematical definition, but in few words, it just means that an edge is a gangplank if it tends to keep apart two nodes and their respective neighborhoods more than bringing them together. So using this notion, we use clustering algorithm on the distance graph of the word cloud. And our objective function is to maximize the number of gangplank edges between clusters and minimizing the number of gangplank edges inside each cluster. So more details on the poster. And we basically follow this three-step cycle. We do not set a predetermined number of clusters. We just take some seeds and then let grow the clusters around it, and then exclude all nodes connected by gangplanks. And we go on until one cluster is formed, and we see another again, and so on and so on. And in the end, we have hard clustered all the distance graph, and each cluster should correspond to a possible sense of the word in our document. So this was a very brief sketch of the algorithm. More details are on the poster, and thank you for your attention.
Hey everyone, I'm Luigi Di Caro from the University of Turin, and I'm going to present you this paper. It's a kind of overview of a recently funded project on distributional semantics by Compagnia di San Paolo. And so basically, the idea is that currently computational linguistics is able to extract information from distributional analysis over word occurrences, basically. And so this is done, this actually works because of the distributional hypothesis that all we know. So words that co-occur basically share similar meanings. And but words are related to what the linguist linguist Ferdinand de Saussure called signifiers or symbols or whatever. And so conventions to link shapes, words with meaning, with concept. But actually, words are empty boxes, and so even if they have some distributional property, and so we can extract some meaning, they are empty boxes without content. Of course, these distributional analyses are used to extract semantics and applied in many tasks, and they are applied to build many semantic resources. And so basically, just a brief overview, that distributional semantics is actually a kind of distributional analysis, a kind of data mining task where a language is seen as a grammar-based type of data, so it puts order, but also it does not scale with the length of sentences and phrases, for instance. To produce, it produces basically matrices and tensors which are sparse, and it's a problem from a distributional analysis point of view. And so just a brief slide about the similarity, that is an essential brick in the computational linguistics scenario, but it is also important for us as humans, because we know similarity because we use it every day. So when we don't know something, we make comparison with what we already know, and so the concept of similarity is very important for us. And in computational linguistics, there is some computation of similarity, but this computation is about similarity between lexical entities. Okay, and it is there is a gap between the two things, and so the idea, going quickly, so basically the idea is to use existing semantic resources to enrich input corpora. Okay, with this, so we actually replace words with semantics that have been already extracted from and existing in existing semantic resources. And so in this way, the distributional analysis is done later. So after this this step, so we apply distributional analysis on the semantics that has been associated to the words in the text. And so basically the idea is to correlate semantic facts associated to the words in the text instead of correlating lexical entities. So it's a kind of distributional hypothesis, but not done in the lexical, let's say, dictionary, but in a dictionary made of semantic features, basically. So this is a very simple architecture, but large corpora are analyzed linguistically, and basically words are replaced with these sets of semantic information coming from the semantic resources, and then later we apply the distributional analysis. Okay, thank you. Other details at the Foster session.
Hi everyone, I'm a master student at the University of Pisa, and I work at this project with Professor Francis Bond from Nanyang Technological University. So we explored two methods for cross-lingual word sense disambiguation, and specifically we looked at existing parallel corpora, and we tried to disambiguate them, so to enrich them with sense annotation, because there is still a lack of resources in many languages, and everybody in the community could still benefit from new sense annotated corpora. We chose SEMCOR because it's a very well-known corpus. There has been lots of research on this corpus, and is sense annotated in English and has been translated in Italian, here in Trento actually, Romanian and Japanese. And it was mainly annotated through sense projection, which basically consists of projecting annotations from one language to the other through sense alignment. And we used, of course, the wordnets, the Princeton wordnet for English, and then the Italian and Romanian wordnets. And we access them through the Open Multilingual Wordnet, which is a project that connects together WordNets that are standard and follow the guidelines of Princeton WordNet. So sense intersection is very simple, it's very straightforward, and unlike sense projection, it doesn't require any side of the parallel corpus to be already annotated. So what we do instead is make all sides of the parallel corpus, of the multilingual parallel corpus, contribute to the disambiguation process. And we do so by one word at a time. So given, for example, a target word in English, we retrieve its translations in Italian and Romanian in this task, and through the alignment. And for each lemma, we retrieve its set of senses in WordNet, so all possible senses that can be associated to the lemma. Then we simply compare those sets of synsets, and we compute the intersection. So in the end, we will have an overlap, and the senses that are included in this overlap are all the senses that are shared between the three lemmas. And in the best possible case, of course, there will be only one sense, and then we will have disambiguate the target word in both, in English, Italian, and Romanian. But more commonly, we will have that we have fewer senses, so we will have reduced the ambiguity, but not just completely solved. But we find that this is still valuable because then a human annotator can step in, or we can use heuristics or even unsupervised methods, but at least the complexity of the problem has been reduced. So we just briefly compare with sense projection, so with the previous annotation methods used in building the translations of SEMCOR, and with the most frequent sense baseline, which simply associates to each lemma its most frequent sense. There is a bias, unfortunately, in this corpus, so we have a problem with this corpus that is corpus dependent, because in WordNet, English senses are listed according to the sense frequency in SEMCOR. So of course, most frequent sense will perform even better than usual, and it usually performs already quite well. So we are trying to overcome this problem with a new corpus that we are building. I will be happy to give you details in the poster session. Thank you very much.
So now we're done with the boosters for today, and I think we have to ask the organizers what we want to do, because we are quite late, although we kept on schedule with the boosters. So thanks, everyone.
Well, now there is the poster session. I think we can meet here at 6:10 for the General Assembly. At least 35 minutes for the poster session is, I think. Okay. So since we are all members of ILC, we are, of course, all invited to participate to the assembly. It's not a closed meeting, but it's open to everybody. Yeah.